In electrical circuits, capacitors work essentially as very short-term batteries. There are two plates separated by a small distance. A wire connecting an electrical current carries a charge. That charge is allowed to build up on one plate until that charge essentially overflows and shoots over to the next plate. If you've ever experienced a static shock, then you've experienced capacitance. Your body was allowed to collect and store charge, usually by something simple such as rubbing your feet against the carpet. That charge stays in your body until something like your finger gets close to another object that will conduct electricity, usually something metal or another person. There are two main factors that determine how much charge a capacitor can hold: the size of the plate and the distance between the two plates. We don't care. The thickness of the capacitor does not matter, but the surface area does. While a large surface area is good for capacitance, a large distance is bad. In fact, the smaller the distance, the more the capacitance. So you could say that capacitance is relative to the surface area of the plates divided by their distance. The larger the area and the smaller the distance between the plates, the more charge the capacitors can hold. Just like we saw with resistors, capacitors can either be in series or in parallel. They're in series if both capacitors are connected to the same wire without interruption. The capacitors are in parallel if they're on two separate wires that are connected to the main wire by a split or a joint in the wire. And just as we saw with resistors, there are different equations to calculate the total capacitance, but it's going to be the exact opposite of what you may recall with resistors. If you want to find the total capacitance of capacitors in parallel, you simply add up the capacitance of the individual capacitors. So in this case, capacitance 1 plus capacitance 2 will be equal to the total capacitance. If the capacitors are in series, we add the capacitance as denominators in fractions, or 1 over the total capacitance is going to be equal to 1 over the capacitance from capacitor 1 plus 1 over the capacitance of capacitor 2. You can calculate capacitance by using the equation that capacitance is equal to the charge divided by the voltage. You should also be aware of the equation to calculate the total energy stored in a capacitor, and that is the potential energy stored in a capacitor is equal to 1/2 times the capacitance times the voltage squared. By substituting the top equation into the bottom equation, you get the equation that energy stored is equal to 1/2 times the charge times the voltage. You could manipulate that equation one step further so that the potential energy is equal to 1/2 times the charge squared divided by capacitance. While you must memorize the two blue equations, knowing how to combine them to make the red equations can also be helpful. In this question, we're asked to calculate the total energy stored in the capacitor. So we'll be using the equation that the energy stored is equal to 1/2 times the capacitance times the voltage squared. The diagram tells us the capacitance, and while we don't explicitly have information about the voltage across the capacitor, we could calculate the voltage by using Ohm's law and what we learned in the resistors video. When using Ohm's law, our first step is to calculate the total resistance for the circuit. In this case, our two resistors are in series, which means to find the total resistance, we simply add the individual resistors. Or 3 ohms plus 2 ohms is equal to a total resistance of 5 ohms. Next, we use the equation that voltage is equal to current times resistance. The diagram tells us we have 5 volts. So 5 volts is equal to a current that we don't know yet times a total resistance of 5 ohms. So our current is equal to 1, or 1 amp. Between the battery and the first resistor, our voltage stays at 5 volts. Once we hit the first resistor, we calculate our voltage drop, again using the equation that voltage is equal to current times resistance. This time, we don't know the voltage drop, but we do know the current is 1 amp, and we know the resistance is 3 ohms. So our voltage drop is 3. That means all of the wire between the 3 ohms resistor and the 2 ohms resistor will carry a voltage of 5 minus 3, or 2 volts. We also know that the wire between the negative terminal on the battery and the last resistor always carries a voltage of 0 volts. So in the yellow wire we have 2 volts, in the blue wire we have 0 volts. That means the voltage difference across the capacitor must be equal to 2 volts. Now we just plug that into our equation. This funny looking U symbol next to the capacitance means micro, or 1/1 million. So our equation would be the energy stored is equal to 1/2 times the capacitance, which is 2 times 10 to the negative 6th for 1/millionth, times the voltage, which we discovered was 2, squared. If we do some math, the 1/2 and the 2 cancel out. 2 squared is equal to 4, so our energy stored is equal to 4 times 10 to the negative 6, or 4 microjoules. In this equation, we're being asked to calculate the total capacitance of the circuit. In this equation, if you're thinking the equation for parallel capacitors is that 1 over the total capacitance is equal to 1 over capacitor 1 plus 1 over capacitor 2, and so on, stop right there. That's the method we use with resistors. For capacitors in parallel, we simply add them up. So in this case, it'll be 3 plus 3 plus 3 to give us a capacitance of 9 microfarads.